I'd like to present Marcus Hines and Rob Shakir, who'll be presenting Emulating Network Topologies and Kubernetes, a k8s, right? k8s. I'm always confused about that. We have too much terminology. Marcus is an engineering productivity lead at Google and traveled from Mountain View to join us today. This is Marcus' first time on the NANOG stage as he co-presents with Rob. And Rob Shakir works in Google's network architecture team and also contributes to open source projects and standards bodies. Rob presented at NANOG for the first time in 2011 and again in 2019. Thanks for being with us today, guys.
Thank you very much. It occurs to me I probably should have updated my bio. I do that job, but I also do a bunch of other things now. You only seem to acquire jobs at Google. So yeah, we're going to talk a little bit about some work that we've been doing around emulating network topologies and our use of Kubernetes for that. We're presenting on behalf of both Google engineers as well as the kind of wider open config community, which is one of the vehicles for this work meeting open source. And hopefully, so we'll start out with, let's just run down what we're going to go through. We're going to say, well, why on earth do we want to do this? What are we trying to solve? What's the thing that we're trying to do? Then I'll hand over to Marcus and he'll introduce K&E and talk about what we're actually doing, how that works. And then I'll come back and we'll try and talk about a real world use case. So something that we're actually doing with this, what's the thing that we're trying to achieve? Are we meeting some of the goals that we laid out at the start of the presentation? So, quick disclaimer first. Marcus and I are up here on the stage, but we're presenting on the behalf of a ton of engineers at Google and elsewhere. These folks are really talented. They've made really great contributions that have really driven this work forward. And I think we've really seen in this kind of overall ecosystem the real benefits of open source, of getting views from different places, being able to share the ways that we want to iterate on things and really drive new innovative approaches that work for both us as a network operator, as well as from other network operators, and as well as equipment vendors, to really build a good ecosystem around this. And it's a real testament to think how far we've come as some of the industry of getting into open source, to how these collaborations are growing. But absolutely want to call out the talented folks that we work with and make sure that they're acknowledged as to we're just up here doing some marketing for their work. So why do we want to look at some form of network emulation? Why do we want to look at something that gives us a way to spin up nodes in a different way? And kind of take a step back to what are the things that we're often doing. Of course, we are always adding features to the network. We kind of say, oh, like, okay, if we only had this one thing, then things would be simpler, or if we had this one thing, then things would be more efficient, or we could reduce the cost of the network. So the reality is that we're always going to be introducing these features. And so we want to find out ways that we can make the process of introducing features as low cost and as fast as possible. And for many of those features, there's some of them that do depend on hardware and having, exact like chips burnt or new silicon architectures or new hardware layouts that we would need to be able to drive that work. But many of the things that we're doing, and especially when we're evolving the fleet that we've got in the ground, are of course things that are done in software, or they're things that we can emulate in software. So we really want to say, how do we get to the stage where rather than having these like array of labs that each developer kind of has to time share onto, we can say, how do we just basically make that such that we can have an infinite number of topologies, at least one per developer. So you're not sitting there waiting for the topology, or you're not sitting there thinking like, oh, well, when I get the lab equipment, I'll do this, or you breaking something doesn't block other people. So we really want to be able to have that as a basis for moving network development into the same way that we think about software development. I don't have to think about software development, can I get to the compiler? Can I run this on the machine, right? I just go do it, and then I get to iterate on it in my own space. So this is a real enabler for kind of the velocity of adding features to the network. So once we've added those features to the network, though, we also want to be able to say, well, how do we robustly and repeatably test those features? So we've got a set of things that we're running on the network. Maybe we're evolving them. Maybe it's an existing network. Maybe we're changing something in there. Of course, we need to be able to test them. We need to be able to test them before we deploy them. And the kind of theory here is that if we would take those tests and we say, well, we can run them on hardware. Of course we can. We've all built labs, and there's large lab infrastructures that we've maintained for many years, but they're pretty fragile. Hardware fails, fibers fail, the power fails. All these kind of things kind of stop us getting to the state where these tests are easy for us to repeat, easy for us to keep robust. A test failure happens, and you say, well, is it a hardware flake? Is it something to do with a failure in the actual infrastructure? Was it that actually the lab wasn't in the state that it should have been, even if I've got software that's trying to make sure that it is? And so really by being able to say, hey, we're going to take these virtualized topologies, we're going to be able to turn them up really quickly, which means that we can start a new one every time that we want to. We can manage their life cycle, so we can take them from, turn up a bunch of brand new devices, emulated devices, and then kick them off in hermetically with a hermetic set of inputs to be in a known state. That kind of gives us a way to be able to test things differently to how we would have done before. We can start to think about, well, actually, like we can run all this test suite, all this set of cases against these emulated topologies. That gives us a way to know that the tests are good, and then we can move on to the hardware. It isn't now that we have to wait for the hardware or fix these flakes to know that the thing we're developing or the thing we're regressing is good. And it opens up a huge new set of new opportunities as well, which is like sets of things that are really difficult for us to emulate, to do in physical infrastructure. So things like link impairment. Well, what do? I kind of go and bend the fiber a bit, but I can't really do that repeatably. I can't really do that in a way that creates those non-happy path scenarios. So another opportunity we were looking at, and thing that we wanted to solve in looking at this kind of infrastructure is, can we start to think about, well, if it's in software, can we have fault injection? Can we have ways to be able to introduce new impairments to the infrastructure that let us validate things? So we've now kind of like developed some tests that are giving us some confidence internally, but for a bunch of our network deployments, we also have a company boundary in the way. We have a supplier and we meet with the customer. And a lot of the compliance that we've had in terms of those specifications is humans interpreting text, whether it's RFCs or RFPs. How we read them, we have our own interpretation. And at the end of the day, we will have all seen cases where we've interpreted things differently, so the infrastructure doesn't actually work how we want the product, it doesn't do what we need. If we move that into code, look at the way that we can say, well, here we've got something like an automated test case that gives us a clear contract. But we also, that gives us some part of that problem. But we need to have some common way that we can actually run that. I want to be able to give something to a supplier and say, hey, just run this thing, and it turns up from nothing to your product running in some scenario I care about. And that then has a set of testing that runs against it, that when that passes, that's compliant. I'm happy with it. So we need to be able to have that we really want to look at a way to have that packaging to reproduce scenarios in a way that we can also introduce new vendors. We don't want to have to re-specify this across different vendors. And then once we kind of look at these sets of sort of compliance and individual products, we want to also be able to look at scale. And if we want to go and have a production scale lab infrastructure, it's going to cost the same as it cost, or somewhere similar to what it costs to do it in production. And so you maybe have some of these scaling environments, but not that many of them. And when you build them and they've got a fixed topology. And so you have one environment, but now you've got the problem of production doesn't really look like that because it's in between these two states of the old way we were doing things and the new state of doing things. So we want to be able to actually flexibly produce these topologies at some scale. We want to be able to do a what if about what happens if I had the whole new design, or what happens if I'm in some hybrid. And this kind of the thinking about moving to some more emulation and more use of software in this area was to say, well, can we go to production scale and beyond it? And verify at that scale. So this is really the set of problems. And I'll hand over to Marcus, who will explain what he did when I moaned as a customer.
So y'all did have a slight preview earlier with the OTG side of things, but now we're going to actually talk a little bit more in depth on what K&E is and why we came up with it. So all those things that Rob really talked about is what started us down this path of trying to answer a question of, how do we provide a virtualized environment that actually scales with our needs? And I think that's one of the biggest pieces of why we ended up at a place with Kubernetes, and the ability to scale from a single developer environment on a laptop all the way up to a 1,000+ node worker pool, holding thousands of actual container nodes, simulating large scale networking. We really appreciated the k8s environment around lifecycle management, and that is was one of our big blockers when we first started doing emulation platforms was we were reinventing lifecycle management. The various vendors would provide us with a VM, but VMs are not a stable API. Every kernel version, every new compilation can introduce new dependencies on the host that you're actually about to try and run that VM on. And whereas Kubernetes containers have mainly abstracted a lot of those details away. And so that's where we ended up with, hey, let's let Kubernetes do what it does good, which is lifecycle management of containers. Let's get the vendors to partner with us on developing real container-based network OSs, and then we'll work on providing the actual wire transport to move the L2 frames across a emulated network. So, when talking about container first, again, when we look at VMs are very fat. They're their own OS. I mean, they're the full stack of OS. Whereas containers, can be very low consumption, can strip off most of the things that really aren't core to the functionality that we were really talking about. Because most of the time, when we're talking about what are we testing about a network OS, we're really talking about the control processes, right? We're talking about user space processes, nothing magic past that. There is a forwarding plane element, but that forwarding plane element isn't really, normally is implemented by the vendors in their own user space emulation as well. The whole point is to not use the Linux kernel. You actually want to, emulate some form of an ASIC. By using k8s, we also have a clear standardized API for how the vendors package that up. We say, hey, we're going to provide you with this set of emulated interfaces. When you boot, you map those internal provided Linux interfaces to your respective hardware represented interfaces. We have obviously standard image format, and we have a standard lifecycle management system. One of the other big pluses in the k8s world is the operator pattern, and so we've actually worked with the vendors not only to give us the images, but almost all of them have actually completed implementing their own operators. So you even get the vendor ownership when using K&E of not only do I not have to worry about how to bring up the container, but the vendor actually owns that and maintains how they bring up their containers. The last little point is, well, we do also still support VMs because there are certain OSs which are not container friendly. We still have a mode for that. It's not generally the one we go with, but obviously, in the network operations world, we know we are stuck with things for sometimes longer than we'd like. We definitely, when looking at k8s, it was leverage everything we can. And so when it came to, well, how are we going to do these network wires? How are we going to do the L2 connectivity between the containers? Well, we stole what we could. And we found a really good partner with Network Op, and who built MeshNet, which is originally was a VXLAN/VETH-based L2 CNI plugin. And we worked with them to modify it slightly so that it worked with us in K&E. And so basically we can fire up a base just k8s cluster, deploy the MeshNet CNI, deploy a load balancer onto it, and then we can just take the vendor container operators, deploy those, and then we can start firing up any topologies we're looking for using just CRDs. Fundamental concept within a K&E topology. Unfortunately, we did pick some bad naming in places because you'll see the word nodes. And when we talk about a K&E node, we really refer to the network node you're actually emulating, not the worker node that the k8s is actually going to drive, run the process from. But basically, we have nodes and links and services. And the node, as we described, can be any vendor container. And the links are simply describing the L2 connection that we're going to deliver between the two nodes. And services are simply going to be your load balance services exported through the k8s from the nodes for providing all the base level SSH, GNMI, gRibbie type services that we support. So where do you start? So unfortunately, all of the vendors have not open sourced all of their container images yet. So it is on the person to acquire your network images. Most of the vendors, and pretty much all the big vendors, support a containerized version of an OS, so you can work with them to get those. Once you have them, you define your node in a simple topology protocol buffer and the services and links, and basically there's a k8s command to both create a cluster if you want to run a local cluster, as well as the k8s create, which will just talk to an existing Kubernetes cluster. So what does that look like? We try to keep it simple. We just have a simple protocol buffer that allows you to specify what type of OS you're looking for, what kind of node, and basically a config element section that just says what container path are you looking for, and then we also allow you mounting configs so that the devices can actually boot with a boot config, and then at that point you can now specify the interfaces, which are going to be, these are going to be the interfaces used by your link to describe how you want to do your mapping. So the interface section here, in this case, we have a Cisco XRD node, and we are simply saying, hey, your ETH1, that's going to be referenced inside the container as a gigabit Ethernet 0000. And you can, this allows actually you to link your, like say you have a actual operational config that actually has specific devices named, you can use this to help you map those so that you can actually kind of keep a, maybe a production-like config, and you could still use that same config interface naming in your emulation. Services, they're just defined. Basically, this is just giving you a mapping to allow you to say, if you want to SSH to your device or you want to connect to an open config GNMI service, we have an, kind of an internal to external mapping. This lets you also normalize. Some vendors run specific services on internally different ports. So this kind of lets you have a consistent presentation when you're coming out of the cluster to say, hey, all of my devices, my GNMI is going to be, in this case, 50,051. Links. Rob and his pictures. So links, we go with just a simple setup of saying, well, hey, give me my AZs. And those are basically going to build, once the CRD gets populated, MeshNet will go to work and actually lay out your VEs between all of those worker containers. And we actually did just actually landed a change to where MeshNet originally used VXLAN. VXLAN has a couple of issues around MTUs and things like that. So we actually replaced that with actually a gRPC wire transport. So this allows us to basically send any MTU between nodes. And so we can support, whatever frame size needs to be there. Also, some interworking with like ISIS, since the Linux kernel itself sometimes will eat PDUs that match specific MACs by going to gRPC wire and pulling the Linux bridge out of that mix. Lets us sends those frames without any issues. Here's a simple topology. Basically, this is a 3-node topology with lags between the devices. And so we just want to show you roughly, this is what we would consider a pretty small topology. It's like, actually, this is one of our simplest topologies we used during our testing of k8s to make sure we didn't break anything. This shows you the node, the node interface, and then the interfaces connected to it through its interface names, through the MeshNet links, and then to the remote side. We have like a simple visualization that basically will produce these topologies based on the provided proto. So whenever I mention the vendors, these are all the vendors that are currently supported within the ecosystem. Arista, Juniper, Cisco, Nokia, and Keysight, have all given us, major props around, working with us not only to give us the container images, but also to provide operators. Keysight especially, if you saw the presentation earlier, big contributor on being able for us to actually have a full production platform for traffic generation and protocols. Additionally, you can actually start any container you want. If you specify just what we call a host node, you can start up any Linux container that you may have. So this also lets you take it not only to just like kind of a functional test, but you could actually have a full integration test here as well, because you could bring up any of your own service controllers in this environment, and that would talk consistently across everything.
Okay, so that's K&E in a nutshell. I'll talk a little bit now about what we're actually using K&E for. And so this is coming back to some of the use cases I was discussing at the start. What we'd like to be able to do is programmatically, repeatedly validate network deployments. And of course, when you think about that statement, you think about muskrat, right? Which is an on-datra. Of course, you don't. What you do is you come up with a terrible backronym, and then you figure out, oh, it sounds like an animal, and so then you've got your logo canned. So that's what we did. To much confusion of lots of muskrat pictures around the office. So OnDatra is the Open Network Device Automated Test Runner and API. I told you it was a terrible backronym. And essentially this is in the wider ecosystem we've been working on, is a way to be able to have a test framework that is very user-friendly I'm a network person wanting to do some network testing, and abstracts a lot of the details away from you. So what the framework breaks down into is we have a set of tests that are expressed in code. This is the part of the kind of consistent contract that we're trying to provide. We write them in Go, and the network teams that want to write tests own this test case. What the test case looks like is it's calling a bunch of OnDatra APIs, and those APIs expose some of the sort of fundamental parts of the topology that you might need to do. Details about the test bed. I'm dealing with an abstract device. Tell me what this port name is because I actually need to know at this point in time. Or push some configuration. Read telemetry from the device, do some operation like upgrade the OS or prod a daemon that's running on the device, and then the traffic generation. So your test case looks like essentially a relatively opinionated set of APIs that give you a clear, sort of readable test case to be able to express your test in. OnDatra itself then takes those sets of capabilities, expresses them through a binding into the actual infrastructure in the lab. So that's the physical or the virtual resources that the tests run on. So the binding layer here is something that we'd specifically introduced thinking about, well, okay, we might want to do this not only in our own environment, not only in other people's physical environments, but also in virtual environments where we want to abstract some of the differences between the fact that there might need to be a reservation system in a physical topology that says, well, can I get hold of this device? Versus in K&E, well, you've probably got your own thing. So the answer is, yes, you can have your own device. So the overall breakdown here is a set of infrastructure that gives us a way to be able to express these test cases that takes into account that we've got this emulated and physical infrastructure to be able to accelerate that development. And what that breaks down into is that something that we're building is what we're calling a functional or standalone testing. Essentially, we're trying to build a set of tests that give us a way to work with simple topologies, whether they're one device or small number of devices, to be able to validate the functionalities of the device. You can really think about this like, well, I've got this black box sort of function that came in that was the network device, and I want to think about how do I unit test it? And how do I then start to integration test it? So that as we move forward, we can think about the changes in that infrastructure running through a CI/CD pipeline in the same way it would if it's code, but give us some way to, when a test fails, we don't have to say, well, okay, this complex topology failed, let's go debug it. It's like as simple as, well, this unit test failed, so of course all the other things fail, so let's start there. And OnDatra gives us the way to be able to express these things. OnDatra, the infrastructure, provides a way that we interface with the different parts of the system that are going to deal with the test. So for example, if I run through a kind of basic test case, the test case will come up. Before the user gets any of their code run, OnDatra makes a reservation call, gets whatever the underlying system is. As part of that reservation call, one of the things we do is reset the configuration of the device to some known base config that you can start with. And then OnDatra allows you to step through the test case, abstracting from you what the device under test is, and the automated test equipment, like traffic generator, that would sit alongside it, that help you do some black box validation of those devices. So this is something that we've been using K&E for helping our development of, and OnDatra is the way that we realize it. Did not expect there to be a white slide there. So how does K&E help us in this? It gives us a way, as I kind of said, that we want to be able to start out with, I've got this new feature that I want to run on the network device. I'm going to start out with, well, I spin it up on my laptop. I have K&E running. I have XCSC or another traffic generator. I have my device under test container. And I can iterate. I can experiment. I didn't use anyone else's resources to do this. And we can then take those changes as we commit them, put them into open source repository. We're building this test like around OpenConfig, and you kind of think about the way that we get some of the other abstraction of the devices through the standard data models and gRPC services we've been working with to make these test cases portable across different implementations. So now we're integrating these test cases into OpenConfig, but now you can just run this like you would run any CI/CD testing. So you say, well, I can launch it with a GitHub action, start up a VM in GCP or in wherever you'd like it to be, spin up K&E on that, and then create the same topology and have this as a repeatable process that runs. So we're going to do a demo. Unfortunately, Greg, who is the tech lead for Ondatra, wasn't able to be here, so we're going to run through a video of the demo, and then we'll come back and have some closing thoughts. So I'm hoping this is just going to play. Okay. Any guidance on how to get the video to play? I assumed it would just autoplay. Okay. Audio?
So first we set up K&E. Before we set up K&E itself, we first need to install 4 of its dependencies. I'll start by verifying that I have Go installed. I need Go version at least 1.18. Here I have 1.19, which will work fine. Next, I'll check that I have Docker installed. Docker run hello world, and I do indeed have Docker installed correctly. Third, I'll install kubectl. Kubectl is a command line tool for interacting with Kubernetes. I'll download it and install it. Done. And fourth, I'll install Kind. Kind is a tool for running local Kubernetes clusters in Docker containers. I'll install Kind version 0.14. Now I have the dependencies of K&E installed, and I'm going to install K&E itself. I'm going to clone the K&E GitHub project. I'm going to cd into the K&E CLI directory. I'm going to build the K&E CLI. That's the only part of K&E we're going to need to build here is the CLI tool. That has been built, and now I'll verify that K&E has been installed and set up correctly. Now we will create a network topology with K&E. The network topology we are going to create in this demo is available as an example topology in the K&E GitHub project under the name 2-node Ixia CEOS. It contains 2 nodes. The first node is named OTG. OTG stands for Open Traffic Generator. Open Traffic Generator is a new API for generating test traffic developed by the makers of Ixia. So this is our node for generating traffic. The second node is the Arista node. It's our device under test. Here it is specified to be an Arista device that is running CEOS. It is bootstrapped with a fairly minimal config, referenced by this file, that configures its interfaces and ensures GNMI is set up. Finally, the topology creates 2 links between interfaces on the OTG and Arista nodes. Before we create a topology, we must first deploy a Kubernetes cluster. That is done with the K&E deploy command. K&E comes bundled with an example deployment definition, kindbridge.yaml, that uses kind to create the cluster on your local machine. With the cluster deployed, we can now use the k8s create command to create our topology. Here we pass the 2-node Ixias CEOS topology that we referenced before. We can use kubectl to see the pods that are running in the topology. Here you can see a pod for the Arista DUT, one for the OTG controller, one for each of the OTG interfaces, and so on. You can also take a look at the running services in our topology with kubectl get services. Now we will look at some ways you can manually interact with a running topology. You can push config to a device with the k8s topology push command. For our demo purposes, we will push the same config that is already bootstrapped to the device, so it will just be a no-op. Done. You can also SSH to a node with the kubectl exec command. We have now logged in, and we can run an arbitrary command like show version. We can also verify GNMI is available and working on the device. First, we'll install GNMI CLI from the OpenConfig project. There it's installed. If we looked at the config on the device, we would see that the username and password set up for the GNMI server is just admin. So let me set those here before I run my GNMI CLI command. GNMI CLI is also going to expect an IP address and port for the GNMI endpoint. We can look that up with kubectl get services. We see the Arista node has an external IP of 192.168.18.54, and it is running, GNMI is running on port 6030, which we could also look at. We could also see that from the config. So with that information, now let's send a query to GNMI CLI to that IP and port. And we're just going to query the state of the interface named Ethernet1. And there we can see the GNMI notification for the state of that interface. The final piece of this demo will involve running an Ondatra test on our k8s topology. We start by cloning Ondatra from the GitHub repo. Now that it has been cloned, we will build Ondatra. The Ondatra README says first to run go generate, which auto-generates some of Ondatra's APIs. Now we run go build. It is built successfully. To run an Ondatra test on k8s, we first have to configure the k8s binding. Ondatra tests can run in many different test environments, k8s being just one. Each one of these environments needs a binding that lets Ondatra know what the available devices are and how to access them. Our configuration for the k8s binding, in this example, is a simple 3-line YAML file. It specifies the username and password used by the device, which here is just admin, and the k8s topology on which the test will run. That's all we need to configure the k8s binding. Now let's look at the test we will be running. Every Ondatra test needs a test bed, which specifies the physical resources it will need to run. The resources are specified as abstract constraints, not specific physical devices. The binding then resolves those constraints to specific devices at runtime. Here is the test bed. This is a simple test bed that requires one device under test, or DUT, and one piece of automated test equipment, or ATE. An ATE is a device that generates our test traffic, and it constrains the DUT in the ATE to be linked on 2 ports. Finally, let's look at the logic of the Ondatra test itself. Test main is the entry point for Ondatra test execution. Every Ondatra test begins with a test main that calls ondatra.run tests. This test has 3 test cases. Test config, which tests our ability to push vendor config to the device. Test GNMI, which tests our ability to query the DUT's GNMI service. And test OTG, which tests our ability to configure the Open Traffic Generator node and query information about it via GNMI. Here is the test command we will execute. When we run any Ondatra test, we pass a flag that specifies the test bed we want the test to use. And because we're running on k8s, we also specify a flag for the k8s config, which I showed earlier, which here lists the username, password, and k8s topology. We now run the test. Here we see the devices from the k8s topology reserved by the test for the test execution. And the test passed. That concludes our demo.
Cool. So hopefully that shows the set of tools kind of working together, going from, we'll admit that we cut out a little bit of time waiting for things to build because it seemed like sitting here watching it actually build was a bit too much, but it's close enough to real time that you can kind of go from nothing to a deployed set of infrastructure on your machine and run and write. You saw some very simple test cases, but this set of APIs are extended to cover much more, and protocols, other interfacing with the device, other telemetry retrieval type tasks. So that sort of lays the foundation for this wider concept that we've been aiming for some time, which is this kind of idea for test-driven design, test-driven development for network devices. So essentially, we want to be able to start out with, okay, we want to do something new with the device. We want to be able to go and then design the API, whether that's a new open config model because it's a configuration service or it needs some new telemetry, whether it's a new gRPC service like GNOI or a new even kind of routing protocol like gRibby. Go and design the API, look at the way that we develop tests using Ondatra, so using either the inbuilt helpers that Ondatra has, or Ondatra gives you a way to be able to access things like raw gRPC connections to devices so that you can iterate on new things, and ideally test that against a reference implementation. So we don't want to have to wait for there to be a commercially available or a production quality implementation before we start looking at how this thing should work. We want to get those learnings of writing code earlier and writing the implementation earlier on. So we have a couple of reference implementations that are open source. There's Lemming, which is a reference implementation of a network device that has a GNMI server, a gRibbie server. It's got support for BGP right now. It's got an emulated data plane that can actually pass traffic. And so this gives us a way to be able to quickly start to look at like, okay, we want to be able to play with this feature, this thing we're thinking about. Let's go prototype it. Let's figure out what it looks like. Let's look at what the API should do. Let's write the test that gives us the compliance contract, gives us a way that we don't have to go and write an RFC to go and describe what everything does, and actually much more coherently describes what should happen and more completely describes what should happen in that. We also have an implementation of a reference traffic generator that I think was mentioned earlier, that essentially it's not meant to be a production quality thing, but if you're looking at a new way that your new protocol or a new packet format that you might want to play with, gives you a way to be able to add injection of that without necessarily having to wait on other requirements. And then that gives you the compliance contract to go and work on the production implementation. You say, okay, I understand what it should look like. I understand how to spec it. I can explain it to somebody else. I've worked out the nuances of it. And now we can go and look and implement this on a production device. And reuse the things that we've discussed. Ondatra for the test case. K&E for the way that you use the actual commercial implementation that you could take. And deploy that into production based on this pipeline, which we think gives you a much quicker way and a much more coherent way to do feature development on network devices, and builds on this kind of the overall concept of moving to programmatic interaction with devices, which the OpenConfig project has been working for the last 7 or 8 years on. So thank you very much. This is Marcus and my email address. Everything that we mentioned is somewhere in the OpenConfig GitHub. There's probably some description of it on openconfig.net as well. Thank you very much indeed.
Yes.
Well, thank you very much, Marcus and Rob. That was a great presentation. Thank you. Oh, we have a question? We do have a question. Okay. A little slow.
I'd like to ask, so if you have a new vendor who wants to become supported from the K&E perspective, what steps should they do to get that support added to K&E?
You want to take it or me? Okay, I'll take it. So in general, the barrier to entry is if you can produce a container, that's step one. Once you have a standard container at that point, in K&E there is a node specification and a node interface. And the really lightest way, and the way you should probably bootstrap in, is to say, fulfill that interface. So you literally just write a Go module which fulfills 6 or 7 methods of basically you need to create a couple Kubernetes objects and basically your service and your node definition. And we actually do provide a default implementation, but most people do need to tweak that just a bit. And at that point, you need to tweak the topology proto to add your new vendor type. And at that point, that's pretty much it. Now, again, as you go forward, if you want to productionalize that, then learning a Kubernetes operator and then having a full Kubernetes operator deployment is obviously a better long-term, but yeah, all you need is that.
Any online questions, Michael?
Yeah, we have 2. Well, it's actually 1 from Matt Peacock. Does ONDATRA allow you to specify link management in your topology, or even link always perfect? I.e., can you add lose latency to links?
So that's one of the reasons that we went and have implemented the gRPC wire. Essentially, with Beeth, we're kind of a bit constrained as to what we can do, but it's an extension that now we've landed the gRPC wire implementation. We're starting to think about, well, there should be this injected latency, there should be this injected impairment, and we've even started to think about, well, should there be ways to be able to have like lower layer errors injected? So can I start to have like bit error rate from what would be a transport system or something that the optic might see, so that we can start to test those paths. But it doesn't today, but it's on the plan.
Okay. Clear.
Okay, thank you again, guys. Thank you very much.